We just have the 3 more slides from the previous lecture regarding the two-stroke scavenging. Okay, we explained last time the two-stroke cycle and revised the four-stroke cycle and knew the differences between them. We were talking about, at the end of the last lecture, we were talking about the volumetric efficiency and charging efficiency. And we mentioned that for the two-stroke, we have scavenging efficiency and the delivery ratio. Okay? Scavenging efficiency, it is the efficiency of removing the exhaust gases from the cylinder and filling it with a new charge. Okay? It's like the charging efficiency for the volumetric efficiency for the four-stroke engine. But we have some issues with the two-stroke, is that as we mentioned, we have no separate stroke for the exhaust and we have no separate stroke for the intake. Okay? And we rely on the intake entering from the intake port, okay, to displace the exhaust so that we can get a fresh mixture. So a fresh mixture is usually a mixture of new air and fuel and the exhaust from the previous cycle. Okay, and also part of the cycle is a new charge can escape through the exhaust port. So for the two-stroke, we define a delivery ratio term, okay, and the scavenging efficiency term. Look at the differences between them. Delivery ratio is the mass of fresh charge delivered divided by the reference mass. Okay? And the scavenging efficiency is the mass of fresh charge retained divided by the total mass trapped in the cylinder. Okay? Does it seem there is a difference between both of them? Usually, you get them both mixed up, okay? But if you concentrate on their calculation method, you will get the difference. First of all, what is the reference mass and the delivery ratio? The reference mass is density multiplied by the displacement volume, rho naught times Vd. Rho naught is the density at the standard conditions. Okay? What is the mass of fresh charge delivered? It is the fresh charge that we add to the system. Okay? Does it have to be all retained inside the cylinder? No. Part of it might escape through the exhaust port. Okay? So, if we are talking about the overall mass that was, the fresh charge mass that was delivered to the cylinder, we will be talking about the delivery ratio. If I intend to know what percentage of the fresh charge was retained compared to the overall mass inside the cylinder, we will be talking about the scavenging efficiency. So, for the delivery ratio, we divide by the reference mass, which is the mass of the standard mass of the fresh charge alone. But in the scavenging efficiency, we take the overall trapped mass inside the cylinder, including the fresh charge retained inside the cylinder and the residual exhaust inside the cylinder. So, can the delivery ratio can the value of the delivery ratio be more than 1?
No.
It can be more than 1. When, if you are talking about turbocharged engine, forced induction. Okay? But can the scavenging efficiency be more than 1? Never. Because you always divide the mass of fresh charge retained over the total mass entrapped inside the cylinder, including the fresh charge retained and the residual exhaust. The maximum value for the scavenging efficiency is 1, which means that all the exhaust was discharged from the cylinder and all the trapped mass inside the cylinder is fresh charge, which is an ideal case that never happens. Okay? So, the scavenging efficiency can never exceed 1, but of course we need it to be as close as 1. Okay? Because if it's lower than 1 by far, then it means that the portion of the fresh charge inside the cylinder is very low and the residual exhaust is very high, which means that we will get very low combustion efficiency and very low power. So to know the scavenging type, we have 3 main types. The first one is the cross flow, which is the one that we discussed earlier when we explained the two-stroke cycle. Cross flow means the intake port and the exhaust port are on the same level in front of each other. Okay? So what makes the fuel, the pressure charge, do not exit right through the exhaust from the intake? We add this curvature in the piston itself so that we force the pressure charge to go up and try to displace the exhaust through the exhaust port. Okay? But of course, part of the mass can just not go straight up and go sideways through the exhaust port. Okay? This cross-flow scavenging results in a low scavenging efficiency and residual exhaust mass reaching 15%. So 15% of the fresh charge is residual exhaust. Okay? The next one is the low scavenging. From its schematic, for the air to enter and exit through the exhaust port, which is right above of it, it has better chances. Okay? So the air enters, of course, it enters the intake port with momentum and velocity. Okay? So it can't reverse right away to the exhaust. So it will go to the end of the cylinder and move up and displaces the exhaust out. This way reduces the residual mass efficiency to up to 10% and it has a medium scavenging efficiency. Okay? The third method, which is a uniform scavenging, we add exhaust valve. Okay? And we make the intake port circular around the cylinder. Okay? So when we start the intake, the pressure charge rushes inside the cylinder through the circular intake port and pushes all the exhaust upward. Okay? Making the residual exhaust much less. And we can control the valve timing so that we can close the exhaust valve and not allow a lot of pressure charge to escape through the exhaust port. Okay? And this results in a very high scavenging efficiency and the residual exhaust mass is low, up to 5% only. Okay? For the two-stroke scavenging, if you want to calculate the delivery ratio and the scavenging efficiency, we have two assumptions. Either we consider a perfect displacement assumption or a perfect mixing assumption. Perfect displacement assumption, we consider the exhaust and the intake air or pressure charge like solids. Okay? The pressure charge enters, so it must displace, it must push all the exhaust out. Okay? Is you do not mix whatsoever. Okay? It's like you are pushing one brake with another. Okay, the second brick takes the place of the first, and the first brick just gets out of the system. Okay, so we assume in the perfect displacement that there is no mixing between the pressure charge and the exhaust. Okay, and the pressure charge just pushes the exhaust outside. In this يعني انت اللي كنت طالب ان احنا نخلينا السبت بدل الثلاث وانت جاي متاخر. delivery ratio. احنا قلنا delivery. What was the delivery ratio? It was the mass of pressure charge delivered divided by the reference mass. We stated that the delivery ratio can be either less than 1 or more than 1. Less than 1 if it's naturally aspirated, and more than 1 if it's turbo charged. Okay? What was the scavenging efficiency? No, it was the fresh charge retained inside the cylinder divided by the overall charge inside the cylinder. Okay? So, if the delivery ratio is less than 1, it's maybe 0.9. Okay? And we are talking about perfect displacement. What does this mean? It means that the pressure charge delivered to the engine is 0.9 the reference mass. Okay? So it fills 90% of the cylinder and removes 90% of the exhaust outside. Okay? So, what about the trapped mass inside the cylinder? It's 90% pressure charge and 10% residual exhaust. So what about the scavenging efficiency, which is the amount of pressure charge retained over the overall mass inside the cylinder? The pressure charge is 90%, right? And the overall is 90% pressure charge and 10% residual. So the scavenging efficiency equals what? 90%, which is the same as the delivery ratio. So if the delivery ratio is less than 1, then if we are talking about perfect displacement, then the scavenging efficiency equals the delivery ratio. Okay? What if the scavenging efficiency, the delivery ratio is more than 1? It means that the engine is turbocharged. And it means that we are delivering mass more than the reference mass of the cylinder. Which means that all the exhaust gets out from the cylinder. So all the retained mass inside the cylinder is what? Is pressure charge. So the scavenging efficiency is what? 1. So if the delivery ratio is more than 1, then the scavenging efficiency equals 1. There is no residual exhaust inside the cylinder. Okay? What about the second assumption, the perfect mixing? Perfect mixing assumes that before the exhaust gets out, all the intake charge gets inside the cylinder, they mix well with each other, okay, and the portion of the exhaust starts to get out. So the mass inside the cylinder is a mix between intake and exhaust, and the mass that was discharged from the cylinder is still a mix between intake and exhaust. So can the scavenging efficiency be ever 1 or more than 1? Never. It will never be 1 even. It will always be less than 1. And we calculated through an exponential term, the scavenging efficiency will be 1 minus e power minus the delivery ratio. Okay? So, as the delivery ratio increases, what happens to the scavenging efficiency? it increases. The term of the delivery ratio is in the negative. So as it increases, the term E decreases. Okay, so the scavenging efficiency increases, which is منطقي, reasonable, because logical, because what? When you increase the delivery ratio, it means that you increase the amount of fresh charge over the reference mass. So more fresh charge mixes with the exhaust or the residual exhaust. So the retained amount of the fresh charge is higher. Okay? But what about actual scavenging? Which one resembles actual scavenging? Perfect displacement or perfect mixing? Neither of them. It's a mixture between both. Some of the exhaust is displaced with perfect displacement and some of it with perfect mixing. It's a mixture between both of them. And this graph explains the relation between the scavenging efficiency and the delivery ratio for both perfect scavenging and perfect mixing and the actual result. For the perfect scavenging, we mentioned that the scavenging efficiency is the delivery ratio as long as delivery ratio is less than 1. So, as you increase the delivery ratio, the scavenging efficiency is the same with the straight line. Till the delivery ratio reaches 1, then the scavenging efficiency saturates at 1. For the perfect mixing, you can see it's a curve and it never reaches 1. Okay? The solid line and the x points are from an experimental calculations, and the solid line is it's fit, best fit line. You can see that at the beginning it matches the perfect scavenging, okay, for low delivery ratios, okay, and for high delivery ratios it starts to resemble the perfect mixing. It's a part mix between both of them, and also it never reaches 1, because you can never adjust it, so all the exhaust exit from the cylinder. They are still gases, so mixing will occur between them. Okay, that's it for